Welcome to Quantum Curious, and in this lecture, we are going to discuss different representations of the electromagnetic field, or in particular, the Fock state in this video. So, we know that electromagnetic field have different properties, and these properties could be measured from various experiments. And we have categorized the electromagnetic field into different subcategories on the basis of these measurable quantities. So we know that in electromagnetic field is represented by mathematically by annihilation and accretion operators in quantum optics and various problems related to quantum optics. So we have seen this kind of representation earlier in earlier videos when we were quantizing the given electromagnetic field. So but in real experiments and real world, we could only measure different variables of related to electromagnetic field, like its amplitude, intensity, and correlation functions. So there are some categories on the basis uh, of these quantities uh, and different representations of the electromagnetic field on the basis of these quantities. So uh, these representations have different quantities from each other, and these classes are easy to uh, denote some kind of state uh, to the given electromagnetic field. So we are going to discuss many different kind of states of electromagnetic field, like squeeze state, Fock states, and coherent states, and all of the properties of these of all of the measurable quantities or properties of the field are different from each other. So let's move on to the Fock state representation. So it is a representation with the well-defined number of photons in a given field. So it is denoted by cat n, as could be seen here, and it has this state has well-defined number of photons, and it is an eigenstate of the given Hamiltonian of the harmonic oscillator, that is the Hamiltonian of the given field. And we know that it is also the eigenstate of the number operator. So we could get the overall energy of the given state. And we are here only talking about the single mode state of the given field. So if there is no photon is present in the given electromagnetic field, so the energy in that case is given by h cut omega over 2. So in quantum mechanics, the field could not have energy is equal to zero even in the absence of photon because of the Heisenberg uncertainty principle. So we could write the given Fock state in terms of the vacuum state by applying of creation operators on the subsequent states and rearranging the terms after it. So first we will apply the creation operator on zero state, and we get this number with eigenvalue of 1, and the creation operator has excited the given vacuum state to the excited state above the vacuum state, and again we apply the creation operator on the first excited state and take the value of the square root eigenvalue of the square root 2 and the excited state above the first excited state, that is the second excited state, and we could write this in that form, and subsequently we have this kind of form, that is the second excited state vector in terms of the vacuum state. So repeating this kind of procedure, we get some kind of recursion relation, and we could represent the given state n having uh, n number of photons in a given field in terms of vacuum state as this in given in equation 1. So this is how we can represent any given state in terms of the vacuum state if the given field is the Fock state. So there is a very interesting property related to the given uh, electromagnetic field amplitude uh, in the given Fock state. So we have an electric field amplitude operator, and it is polarized along the x-axis, and the field is moving along the z-axis. So it could be seen as by this operator. So we want to calculate the expectation value of the given field operator or field amplitude operator in the Fock state representation. So surprisingly, it gives the value of 0. So why it is? The field certainly has the amplitude, but the average value is 0 in the given Fock state. So that is quite unusual behavior. So it could be explained by that reason that the given Fock state has well-defined number of photons, but the phase uh, of the field is randomized over the given cycle, that is the 2 pi cycle. So the average of the field amplitude is 0 due to the randomization of the phase. And so there's a kind of uncertainty principle between the number of photons and the given phase of the field. So in that case, we have well-defined photon numbers in the case of Fock state, but the field amplitude has a randomized phase. Uh, so this is because the amplitude of the expectation value of the amplitude uh, over some given cycle is 0. But the amplitude square, expectation value of the amplitude square does not uh, have a value is equal to 0, or that it is a non-zero value. So we could calculate it easily by taking the square of the field amplitude operator and expanding into the annihilation and accretion operator, and making use of the property of the accretion and annihilation operator on the given Fock state. So uh, these values are 0 for the square of the accretion operator and the annihilation operator, but the values are non-zero for the product of the annihilation and accretion operator, and it could be manipulated like this. So the overall quantity, that is the expectation value of the amplitude square, is given by this E squared sine square kz parenthesis 2n plus 1. So we know that the average of the sine square kz over uh, some period is 1 by 2. So we could put this value in the above equation, and we get the final equation as e squared n plus 1 by 2. So this is the fluctuation of the field in the case of the Fock state. So we could see that if there is no photon, there is still some energy of the field, and the fluctuation is still present even in the absence of photons. So this is denoted as the vacuum fluctuation. So even if the space does not have any kind of stuff, but there is the vacuum fluctuations, the field that are fluctuating randomly in the given empty space. So the empty space is generally not the case in at the very microscopic level. So there is always some kind of energy and the fluctuation associated with that kind of field, that is the vacuum fluctuations. So we could generalize our single mode formalism of the Fock state to multi-mode Fock states. So we have multi-mode number states, and it is represented by the cat, that is the product of all the cats of all the modes of different modes, and the annihilation and accretion operator associated with the different modes commute with each other. So that is why it is possible to write the overall the entire field vector in terms of products of the field vectors of different modes, and it is the uh, uh, eigenstate of the given operator, that is the number operator of the different modes, and it is written in the case of the summation. So it gives us similarly the value of the n, that is the number of photons in different modes. So subsequently, we could define the Hamiltonian of the entire field, and it is just the summation of the number operator of the different modes, and we could write as we have seen in the single mode case. So it is also uh, the given field or vector uh, that is given by the cat n, and parentheses show that it is the state vector of the entire field. It is also the eigenstate of the given Hamiltonian of the field, and it gives the value of this kind of stuff in the energy of the given field, that is the entire field, in the case of this. So we could also define the given field in terms of the uh, vacuum by applying the similar results, that is a similar process that we have defined earlier in the case of single mode, and we could generalize it uh, to the multi-mode case. So we could write the number operator, the number state of the entire field in terms of the vacuum field. So this is for today. We have described that what are Fock states and what are properties, and how is it different from classical states, and we have also described the vacuum fluctuation, that is the fluctuations associated with the zero photons. And in the last, we generalized our result from the single mode to the multi-mode case. So that's it for today. See you in the next video. Bye bye.